Everybody, it's Mr. Patron, and in this video, I'm going to take some time to go through the remaining notes on your lesson 3 from this unit, the Voltaic Cell Virtual Lab. So you just work through the lab with your groups, and now we're going to just kind of go through the last bit of slides that are related to it. I'm going to share my screen and get to this. So once again, we just worked through this virtual lab. We saw a few different reactions going on, and you answered some of these questions together with the group. We'll go through essentially what you saw. So first off, we'll recap these voltaic cells and what happened in this simulation. So a voltaic cell is essentially a chemical version of a battery. There's two types of electrochemical cells we're going to be dealing with. This is the first one. So a voltaic or a galvanic cell consists of both a cathode and an anode. So these are two electrodes you saw in the notes prior. Cathode and anode are just essentially metal bars, and they're dipped into their metal ion solutions. So you may recall the first setup was for your cathode. Copper in copper nitrate, and then the anode was zinc in zinc nitrate. Okay. So the bar here was copper, the solution was copper nitrate, and then here the bar was zinc and the solution was zinc nitrate. Okay. Now, as we ran this process, you should have noticed a couple things. So we'll start on the cathode side. We'll go one at a time. So the cathode side, the one that was marked by the red wire here, is the location at which this metal becomes reduced. So this is where reduction occurs. And we saw that through noting that ions from the copper nitrate solution were actually coming out of solution and coating the metal. So that was represented by like little bubbles that you saw. That was supposed to add some like texture to this. So as the ions come out of solution, they plate onto the copper bar. And what this actually does, this allows the metal to increase in mass. So the metal itself gets heavier. It's taking on more copper atoms, becoming a bigger piece of metal. And then the solution itself, this copper nitrate, becomes less concentrated because now there's fewer copper ions in the actual solution. So on the cathode side, reduction occurs. And physically what we see is that the copper ions transfer themselves onto the copper metal, increasing the mass of the copper metal bar and decreasing the concentration of the solution. Now, on the opposite side of this, we have the anode. So the anode was represented by this black wire here, and essentially the opposite things occur. So instead of reduction, oxidation occurs. So the zinc metal becomes oxidized in this process. So the atoms from the solid metal start to ionize. So what happens is that the atoms on this metal bar, when they oxidize, they turn into the zinc ions. So you may have noticed that it kind of like changed shape. It lost like some edges around here. So that metal actually lost mass because the atoms on here, the zinc atoms, turned into zinc ions. This allowed it to become more concentrated, the solution. So the bar itself loses mass and the solution becomes more concentrated. Okay, so that was the anode versus the cathode. Quick recap. The cathode is reduction, the metal bar is gaining mass, and the solution becomes less concentrated. And then on the anode side, the opposite occurs. We have oxidation, and this is shown through the metal bar itself, losing mass, turning it into these zinc ions, and that solution becoming more concentrated. Now, one thing to note, and probably the most important piece here for this to actually work at a chemical level, is that the whole idea here revolves around how the electrons move. So I'm just going to clean this up a little bit. Now, oftentimes, well, all the time actually, these systems are connected through a wire. Now the wire here, they're connected on the bottom, but more often than not, you'll see it just kind of like set up on the top. And what this wire does is connect the two pieces of metal, but it also allows for the electrons to flow. So the electrons actually flow through a piece of metal wire that's connected to both anode and cathode side. Now, because the anode is the one that is doing the oxidation, you may recall, is losing electrons. Electrons in this type of system always flow from anode to cathode. So I can draw an arrow that indicates the direction of the electron flow. Once again, it's from anode to cathode. So the electrons are flowing this way. They're going from zinc to copper. So in this case, the electrons flow from zinc to copper. And part of your follow-up assignment is going to ask you how or where, I'm sorry, the electrons flow in these types of settings. And I definitely suggest jotting into your notes, making these little arrows and marking all this stuff up here. So when any voltaic cell, keyword voltaic cell, there's another type that we will get into next class, but a voltaic cell involves electrons flowing directly from the anode to the cathode. Okay. All right, so here's a setup. Then we got a little thing that'll help you remember some of this information. So I'm going to clear that and jump to it. Okay, so you may recall that the first little set of acronyms we learned for this unit was Leo the lion goes grr, and that's to indicate that when we lose electrons, that's oxidation, and gaining electrons is reduction. Now, here's another animal-based acronym that will help us remember some of this stuff here. So as you just saw, anodes contain the oxidation process, and then reduction is found at the cathode. So to remember that, we have anox, so ox, and then the red cat. Just another couple things to kind of help you remember some of this stuff. So keep that in mind, jot it down. All right, now we're going to look at a full-on setup using these voltaic cells, using the actual proper materials. So clear, jump to it. Oh, actually, we're not going to do that just yet. We're going to look at how we kind of evaluate what kind of elements are used and which parts of the voltaic cell they are used in. So you may recall that the cells that you looked at in the virtual lab showed voltage. So voltage, like on a battery, it says like 9 volts or 12 volts or something like that. The voltage that is seen in a voltaic cell happens to represent the amount of electrical current that runs via the oxidation and reduction processes. So when one metal is losing those electrons through oxidation, the other one picks them up through reduction. Essentially, the quantitative amount of electrons totaled up gives you voltage. Voltage, when we look at it, we want to look at it through a positive value. So you did see that one of the values on the last setup actually had a negative voltage. And we want to properly set our voltaic cells in order to give us this positive value. Now, for this to occur, the more active metal has to be one that is being oxidized. And through doing that, it's transferring its electrons to the cathode. How we know which one is more active? We look at this activity series. So table J is in your reference tables. And what this essentially tells us is how quickly different metals are going to react specifically to oxidation. So this table is mainly based on how oxidation works. And essentially the higher up, the more quickly or more apt the element will oxidize. So like lithium, rubidium, potassium, cesium, these are all group 1 metals, alkali metals. You may recall those are very reactive. So it makes sense that these react pretty quickly. Gold, silver, copper, these are all transition metals. You may recall from our studies about the different types of elements, transition metals actually are not very reactive. And like gold, silver, and copper specifically are oftentimes used for like jewelry because of their slow reaction time. So the higher on this chart the element is, the more active it is and more likely to want to undergo oxidation. So how we want to set these up is that the element that is more active, higher up on table J, is going to be declared the anode. And then the one that is less active is going to be the cathode. The anode, once again, is oxidation, and the cathode is reduction. And you'll see there's also a setup with some nonmetals here. We're not really going to focus on that. We're going to focus solely on the metals here. All right, so let's take a look at how this works now. Okay, so you are given a typical Voltaic cell setup. So we've got a couple beakers, we have our salt bridge, we have an anode, a cathode, and a wire connecting the two. Now we want to determine which material is essentially supposed to go where. We have manganese metal, manganese is Mn, a manganese nitrate solution, MnNO3, an iron metal, we call iron is Fe, and then an iron nitrate solution, FeNO3. So first thing we want to do is take a look at our table J and determine which element is more active. So essentially, which one is higher on the chart? And then, as you may recall, the higher on the chart, the more likely it is to oxidize, and therefore should be our anode. So let's take a look. So manganese is Mn, and that is not this one, that's Mg, is going to be here, Mn. And then iron is just a few ticks down on here. So according to this chart, manganese is more active than iron. So if it's more active, it is more likely to oxidize. So this is going to be our anode. And then, therefore, iron is our cathode, as it is less active. So we'll just kind of like jot this in here. So manganese is going to be the anode, that's Mn. And then you may recall that the solution must match the metal. So we have our manganese metal bar. This solution is going to be our manganese nitrate. And then our iron bar is the cathode with iron nitrate as our solution here. So that is just kind of how we would determine what metal goes where in this process. So once again, anode is higher up on table J, cathode is lower. Manganese is higher than iron, so that is where each of these go because of that. And then the solutions must match to their metal. Okay. So now we have the setup done properly. Now we can see how chemically this actually works. Okay. So because these are oxidation and reduction processes, we're going to look at these through the lens of a half reaction. So let's just remind ourselves of what went where. So remember, we had our manganese anode and then our manganese nitrate solution. MnNO3. And then our cathode was iron with a FeNO3 solution as well. Just a note, we'll be seeing nitrates and chloride solutions typically are the more common ones in this type of setup. That's because those solutions are typically soluble in water. So really there's no requirement for what kind of solution has to be near, except the fact that it is the same cation as the metal. and that it also has to be soluble in water. Nitrates, you may recall, are always soluble. Chlorides are pretty soluble for the most part. So those are, that's the reason why we'll be seeing mostly those two as we work through this. But anyway, let's work through how we set up these half reactions. So we have oxidation and the reduction process. We'll start with oxidation. So remember, oxidation forms at the anode. So we're dealing with the manganese ion. So oxidation is the process, and you may recall, this is when charge increases. So here, the anode is the element that loses mass because it goes from pure metal into the solution. We're forming these ions. So we're going to start writing out our reaction using our reactant. So the reactant here is going to be Mn with a 0 charge. Once again, this is coming from, let me rewrite that arrow, sorry. So this is coming from the metal electrode. And then we are producing a manganese ion. So in this case, it's going to be Mn with a 3+ charge. And I'm going to review how we determine this. So we're going to be looking at oxidation states once again. So I'm going to put this up here. So the nitrate ion, remember, so that's one of those polyatomic ions. You may recall has a -1 charge. And this is in table E, your polyatomic ion chart. The formula for manganese nitrate is MnNO3, 3. Because each nitrate has a -1, there are 3 of them in this particular compound. -1 times 3 gives us -3 as our negative charge here. Therefore, in order for this to be a fully neutral compound, the manganese must be +3. So that's where we're getting this charge on this ion from. Just a note, manganese, being one of the transition metals, has a lot of potential oxidation states. So it's not one of the clear-cut ones that have specific rules. So that's something to keep in mind. Oftentimes in these Voltaic cell setups, we're using transition metals. And so the charges are going to vary. So manganese, one of the potential oxidation states, is +3, and that's what fits here. So just a reminder, the metal electrode gives us this Mn0, and then it's turning into the manganese ion in solution. So that's floating around it. So we're adding more into this. Now, because we are dealing with oxidation, you may recall through the half reaction process, when we are undergoing oxidation, because we're losing electrons, electrons are going to be on the product side. So along with manganese, 3+, another product here is 3 electrons. The 3 electrons help balance out the charge. So we have +3, and 3- gives us charge 0, which matches to the charge on the reactant side. So just to clean this up and recap it, we end up with our oxidation half reaction as Mn0 yields Mn3+ plus 3 electrons. The Mn0 comes from the metal electrode, and then the ions are being formed into the solution. So then the metal bar gets less massive and the solution becomes more concentrated. Okay. So that was the oxidation half reaction. Now, reduction half reaction. So similar ideas. Reduction now comes from the cathode, which we recall is iron in this case. And in this process, the iron nitrate solution is transferring its ions onto the iron bar. And these ions are turning into pure iron metal, so pure atoms. So we are starting here with an Fe plus 3 ion, or Fe3 plus, we can write it like that actually, let's keep consistent here. And then that comes from the exact same process that we did for manganese nitrate. 3 nitrate ions, negative free charge, Fe is plus 3, so that needs to be balanced there. Now, this Fe3 plus turns into, once again, the Fe with a 0 charge. So the ions are coming out of solution and plating onto this metal bar. So that's where this Fe0 comes from. Now, the 3 electrons here that were lost happen to end up being gained in this process. So as manganese lost its 3 electrons, the iron the iron ions pick them up and allows them to turn into pure iron atoms. Once again, looking at the charge, Fe 3 plus and 3 electrons, that totals out to 0. We have 0 on this side. And then one more thing to note. Electrons are once again flowing from our anode to our cathode. So they're flowing through this wire here. These are our electrons going from manganese, which loses them, to iron, which gains them. So this is how we would write the oxidation and reduction half reactions for the anode and cathode. I'm going to go through one more example, and then your follow-up is going to be some more stuff like this. All right, so we have a Voltaic cell that is set up using the following materials. We have lead and cobalt metal electrodes, and then 2 solutions, lead nitrate and cobalt. So we want to identify the anode and cathode, and then write the oxidation and reduction half reactions. And we have table J right here as well. So first thing we need to do is determine which element, lead or cobalt, will be our anode, which is oxidation, or our cathode, which is reduction. So we'll find lead. Lead is Pb. Lead is right here. And then cobalt is a couple steps above it. So in this case, cobalt is going to be oxidized, and lead is going to be reduced. So cobalt is going to be our anode, lead is going to be our cathode. I'm just going to note that here. Once again, anode is cobalt, and lead is the cathode. Okay. So now, cobalt is undergoing oxidation. So cobalt is losing electrons. So the oxidation half reaction, we're going to start with CO with a 0 charge. So cobalt here is going to be the electrode that is being oxidized, and it is going to turn into the cobalt ion, CO2+. In this case, we have only 2 nitrate ions here, so CO is going to be 2+, as is lead. And because we're going from 0 to 2+, we must also lose 2 electrons. This would be our oxidation half reaction. And then for our reduction half reaction, that's going to be lead reduction cathode, red cap. So lead starts off with the Pb 2+ ion. So that's in its solution. It is producing pure lead here, Pb0. Then once again, reduction, we're decreasing in charge, +2 to 0. Another way to remember that. And then to balance this charge, the 2 electrons that cobalt lost are now gained by lead. And that is your reduction half reaction for this process. Okay, so your follow-up assignment is going to be some more practice like this. You'll be identifying where different components of a voltaic cell go and writing out these half reactions and answering a couple questions. Reach out with any questions and have a great rest of your day.